Hi everyone, happy Friday. So, I got some really good questions in office hours from some people about entropy and like the deeper connections to reversible and irreversibility and reversibility. So I thought, let's go ahead and talk about that. Now this material, most of this material that I'm covering right here, it won't be on the midterm, the first midterm, but a little bit of it might make it onto the final. Like so it pays to pay attention today. But it is a little bit more advanced, and it's not material that you can find in the book. It's actually material in a slightly higher level physics book. But that physics book really likes the connection between entropy and disorder and uses it. So what I'm going to say is that when it comes to entropy and order versus disorder, the jury's still out on that one. Some people like the analogy and some people don't. So it just depends on who you ask. But I think depending upon the situation, it can be useful to think of an increase in entropy as an increase in disorder in some cases, but I think it can also be misleading. I think the way that we did it, where we think about it in terms of the energy dispersal being shared, that's a better way of doing it. Okay, but what about like that example we did in class the one time where we said, oh, the process, by the way, the entropy is 0 for that process because it's reversible. And what does that mean exactly? So it comes back to this equation here. What this equation says is, it says, okay, if I count up this path that this process takes from one step to the other, and I do the integral in a sensible way, I can get this result for the change in entropy in a reversible process. And I can apply it to irreversible processes by pretending. What happened to that? Did that go out again? Oh my God, super annoying. This is not working again. That's going to ruin my lecture. Okay, so let's see here. Let me make a call really quick. Oh, there it is again. Okay. Hold on, let me just report this though. Hi, I'm in 1425. I'm still having issues with the center projector screen. It's on right now, but it was clicked off for no reason a few minutes ago, and it wasn't working last time. So I just wanted to report this as an issue. Maybe you can take a look at it after class. It might be the actual HDMI cable itself. I'm using the HDMI input. Yeah, exactly. Yeah. Sure, absolutely. Thank you. Right, bye. Okay, so we're okay now. Okay, so we talked about, so we have this equation, and we can generalize the definition of entropy change to include any reversible process leading from one state to another, whether it is isothermal or not. So we represent the process as a series of infinitesimal reversible steps. During a typical step, an infinitesimal quantity of heat dq is added to the system at absolute temperature T. Then we sum and integrate the quotients dq over T. So this is an infinitesimal change for the entire process. Okay, what's the difference between reversible and irreversibility here? Let me show you. And they don't really show this in the book, because I don't know if the people who wrote this book even understood this completely. I mean, it's one thing to say like, okay, this process here is reversible. This can go either way. We can have a process going like this. And I think I want to make this even bigger, because this is like a big point I want to illustrate here. This is kind of like an interesting fact. Okay, so we have to pay careful attention to this. So this is volume, and this is 2 times the volume, and this is for like a gas that's got its going like this, where it started at some pressure here, okay, and it ends at some pressure here, and this pressure is half PA over 2, and this is some initial pressure. And then I'm saying, okay, I can integrate along this path, and it's reversible. I can go this way or I can go this way. So it's a reversible process. So this integral that I use to integrate this can be done, and I have like delta S. That's going to be my integral from 1 to 2, and then we have dq over t. T is held constant, and we add just a little bit of heat throughout the process so that it's infinitesimal heat flow into the system, and then we have integral from 1 to 2. So we integrate this thing along here. But what does that mean? Why is this reversible? Well, let's think about this for a second. When I break this, if I have a gas and it's in some volume, and then I suddenly break this seal, so we got all these little gas particles here, and I suddenly break this open, and I say that's irreversible, okay? So what's the difference between that and, like, say, letting one of these particles out so that it gets out so slowly, and then I say, okay, I just let one out at a time, and it's reversible. Why is it reversible if it happens so much slower and controlled, but irreversible if I just make it sudden? Well, one way to see that is from this integral, because like if I let these gas molecules out one by one, even if the process takes like a really long time, we can guarantee that the pressure will always go down. Because if I let one of these molecules out, I know that there's just a little bit less pressure here than there was before. But if I just break this seal, it's just as possible that maybe some of these molecules collide and there's actually more pressure here. But it's not going to be for long, right? Like let's say like 1/trillionth of a second after I break this seal, no gas molecules have had a chance to escape yet. They're all still in this volume, but then they get even more densely packed in some little area, just for a tiny bit. Well, then that process isn't going to go like this. It's going to actually go like this. Let me find a different color of chalk. It's going to be like opposite of this. It's going to go like this way, where the pressure gets higher, and then it comes back, and it's going to be like kind of jagged. It's not going to be some smooth, clear path. There's going to be like irregularities, but eventually it's going to average, it's going to work out to be just like if we had let the whole thing expand in the controlled way. In an uncontrolled way, it averages out in the end. But technically, we can't integrate a function like that. There's something like, we know how to integrate a function like this. We know how to integrate a function like this, but we don't know how to integrate a function like this. All right? That's what that plot is going to look like. If I zero in on a microscopic enough region of it, it's going to be like not a smooth function. So that's what defines the reversibility versus irreversibility, is can I do a sensible integral here? If I can't do a sensible integral, then it's not really an irreversible process. It's not really a reversible process, it becomes irreversible. But because the two work out to be about the same in the end, we don't worry about these little tiny differences. I mean, here I've exaggerated it so you can see it. But like the variation of this is going to be much tinier than this, right? The pressure, it's going to be like the jaggedness is going to be so minute that you aren't even really going to see it in this plot, really. So because the jaggedness is so minute, we say that it averages out to be as if it was a reversible process. And so we can use this equation even for irreversible processes. Okay? So that's like the mathematics behind that approximation. Does that make sense? How we're, for example, again, if I just break this seal, there's some chance that instead of the particles escaping right away, if it's a small enough time, some of them might get even denser packed here, and then I have that going the opposite direction from this forward direction. But if I control it and I just take one particle out one at a time, then we know it's only going to go one direction, and we can integrate that. Anyway, that's the idea behind the irreversibility. Now, what about thermal equilibrium? So, two physical systems are in thermal equilibrium if there's no net flow of thermal energy between them when they are connected to a path permeable to heat. So thermal equilibrium obeys the zeroth law of thermodynamics, and a system is said to be in thermal equilibrium with itself if the temperature within the system is spatially uniform and constant with respect to time. So systems in thermodynamic equilibrium, they're always in thermal equilibrium. And this kind of relates to the first law too. Remember we talked about internal energy and thermal energy? So review your first law when understanding this as well. But the converse is not always true. If there's a connection between the systems that allows transfer of energy as change in internal energy, but does not allow transfer of matter or transfer of energy as work, the two systems may reach thermal equilibrium without reaching thermodynamic equilibrium. So there is there's a slight definition there and difference there. Since entropy is a function only of the state of the system, we can compute entropy changes in irreversible non-equilibrium processes for which that equation is not technically applicable. We just invent a path connecting the given initial and final states that does consist entirely of reversible equilibrium processes. So that's what I did here. When I ignored this jaggedness, I just made a path that did follow a non-jagged path. Okay? Does that click with everybody, or is that confusing? Anybody have any questions about that? We can't integrate something that's super jagged. It has to be smooth. So we invent a path. We basically take those points, because that's what really happens. There's jaggedness, but we draw a smooth line through it in a process that's essentially a type of interpolation or function finding, like you do in your labs. You take a series of plots and you find a function that fits it. Okay, so and then we invent the path connecting the two states, and we compute the total entropy change for that path. It's not the actual path, but the entropy change must be the same as for the actual path in the end. So we only worry about final minus initial. We don't really worry about how it got there. Okay? That's the key thing there. That's how we get around this complication of dealing with irreversible processes. As with internal energy, the above discussion does not tell us how to calculate entropy itself, but only the change in entropy in any given process, delta S. Just as with internal energy, we may arbitrarily assign a value to the entropy of a system. So we know how to actually calculate entropy, don't we? It's a different formula, though. It's not this one. When we want to actually calculate entropy, it's S equals K natural log of the multiplicity, which is based upon the microstates of the system. So counting number of micro that gives same macro state. That's the multiplicity. That's how we calculate the exact entropy. which we can do. But this only tells us the change in entropy associated with the system. This doesn't tell us S. This tells us delta S. And so that's what they're communicating there. That's the point that they're making for that. Just as with internal energy, we can arbitrarily assign a value to the entropy of a system in a specified reference state and then calculate the entropy of any other state with reference to this. So we can set like the state where there is before this process occurs as like 0 entropy, and then we just calculate the difference, how the entropy increases when this process commences. Okay, so now we have an example. So we've got 1 kilogram of water at 0 degrees Celsius. It's heated to 100 degrees Celsius. We can compute the change in entropy by looking at the final states. And the reason I'm just going over this quickly is because we already did this calculation. So we have mc dt over t. This comes from the heat change. So what we do is we have delta S is equal to dq. So for this type of problem, of which we've already done examples from our book, we've got delta S is given by the differential heat flow, dq over t, but we know what that is. dq is going to be equal to mc delta t, which for the differential form just turns into dt for dq, and then so delta S is going to be mc dt over t, which turns into mc natural log of t from some final to some initial, which we can write as a fraction, mc ln t final over t initial, which is how they got that result there. So t2 over t1. And then you just plug in the values there and you compute the change in entropy for that process. Okay? Just a little bit of review here in preparation for the midterm coming up next week. Okay, any questions about this example? Okay, great. So, there's a little caveat here. When delta S is equal to Q over T can and cannot be used. So you might be tempted to avoid doing an integral by using the simpler expression, but this would be incorrect because it's only applicable for an isothermal process, and so the initial and final temperatures are not the same. The only correct way to calculate the change in entropy is with different initial and final temperatures to use. So we can't use we can't exactly use it this way. We have to calculate the differential dq first, and then we can get the right answer, arriving at it. Okay, a gas expands adiabatically and reversibly. What is its change in entropy? Okay, so we've got an adiabatic process, so there's no heat that enters or leaves the system. So dq is equal to 0. Okay, that's 0 right there on top. And there's no change in entropy in this reversible process. Delta S is equal to 0. So every reversible adiabatic process is a constant entropy process. And the increase in randomness, they like to use that expression as a randomness from the gas occupying a greater volume. We could just say the increase, I don't like that. I'd say the increase in the number of multiplicity, because the gas can occupy more places in a larger volume, so it has a higher multiplicity. That increase is balanced by the decrease from the lower temperature. And what we're saying here is the temperature's lowered, so there's fewer collisions going on. So the temperature balances out, and the system is like in the same state that it was in before. So the change in entropy is 0 in that case. And that's why. Okay, now what about an entropy change in a free expansion? So this kind of goes back to that example I did here where I talked about how if you break this seal, instantaneously we have a free expansion. So a partition divides a thermally insulated box into two compartments, each of volume V. Initially, one compartment contains N moles and the other is evacuated. We break the partition and the gas expands, filling both compartments. What's the change in entropy? So there's a picture of it. We talked about this before. There will be a change in entropy. This is for the reversible process of it, but it's actually irreversible. So for this process, we have Q is equal to 0, work is equal to 0, delta U, and therefore the system is an ideal gas. We might think that the entropy change is 0 because there's no heat exchange, but 20.19 can be used to calculate entropy changes for reversible processes only. This free expansion is not reversible, and there is an entropy change. And we talked about this in our class as well, but the entropy increases in a free expansion because the positions of the molecules are more random than before the expansion. To calculate delta S, recall that the entropy change depends only on the initial and final states. So we're going to look at the difference of the volume. So we can devise a reversible process having the same endpoints as this free expansion, and in general we can use an equation to calculate that. So from the book, there's an entropy change of a free gas, okay? That's going to be in chapter 14, right? And it's going to be entropy change of an ideal gas. So instead of this, we have to use this for the free expansion case. Actually, I'll just leave this here. This is our free expansion, so we're going to have a change in volume, okay? And then we're going to have to use this expression. So we have delta S gas is equal to NCV natural log T final over T initial plus NR natural log V final over V initial. And if the case is, if it's done in such a way, it can be done in such a way that this temperature remains constant. But then we can have, if we input heat into the system, we can keep the temperature constant because typically the temperature would decrease if we didn't do anything else. So depending upon how we do it, if we input heat and keep the temperature constant, if T initial equals T final, then this is ln of 1, this term, and that term goes away, and then we're just left with this expression. But there's no way to make both of these expressions 0, because as long as we have a free expansion, we at least have a change in volume. We may or may not have a change in temperature as well, but we at least have a change in volume. And that alone is enough to produce a change in entropy for the system. Okay, so the gas does work during this expansion, so an equal amount of heat must be applied to keep the internal energy constant. So if we apply heat, we can compensate for that work done by the gas. Okay, and then we can calculate Q there and delta S. You can see, and then we can get it from there as well. That's another way to do that. Okay, so to calculate the entropy change of a system in an irreversible process such as free expansion, you must consider a reversible process that takes the system from the same initial state to the same final state. Okay, where it's a nice, smooth transition. And then in an idealized reversible process involving only equilibrium states, the total entropy change of the system and its surroundings is 0. But all irreversible processes involve an increase in entropy. Unlike energy, entropy is not a conserved quantity, so the entropy of an isolated system can change. Remember, we did an example in class where we had the heat flow and the heat from the stone to the ice that melted the ice. The heat was conserved. Q1 plus Q2 equaled 0, but the entropy was not conserved. The entropy was larger for the ice getting melted and turning into liquid than it was for the heat that flowed out of the entropy change associated with the stone, which was negative. The stone itself, by itself, in the process of giving up some heat, its entropy did decrease, but it did not make up for the increase in entropy of the water, the ice that turned into water. And then for this case, with the free expansion of a gas, it's an irreversible process in an isolated system in which there is an entropy increase. Okay, so here we can see this irreversible we have metal, and then we have ice, and then it goes, so a reversible process is one whose direction can be reversed by an infinitesimal change in the conditions of the process and in which the system is always in or very close to thermal equilibrium. All other thermodynamic processes are irreversible. Okay, so that's all of the points that I wanted to make in regards to this chapter. That's it. We're done for chapter 14. The midterm will be over 12 and 14. Next week, we're going to have a review session for in discussion. So make sure you go to discussion so you can review these points and get ready for your midterm next Friday. And then today, for the rest of today, I'm going to actually start talking about fluid dynamics. So this is going to be the next chapter that we're going to do. And we're going to start it today because we have the time. But we're not going to do anything super in detail, just like a basic introduction to fluids. Okay, so here's some basics of, yes. They're not posted yet. I can go ahead and post these though. Yeah, no problem. Whoops. Okay. Okay, and then I'm not sure, did I post this one as well? Let me see if I did. I don't think I did. Okay. Okay, now everything is posted, so we can start on the fluid dynamics. Okay. Okay, so any more questions about that before I start? Okay, great. So although gases and liquids are distinct phases of matter, gases and liquids are not the same phase, but both have flows associated with them, and both obey fluid dynamical equations. Thus, gases and liquids are both fluids. Liquids and gases have similarities and differences. We typically think of a gas as compressible, whereas a fluid is not very compressible at all in most cases. So there are always exceptions to these rules, and this is a very general sketch of how we describe this. Both gases and fluids have pressures associated with their respective depths. For example, roughly speaking, we live at the bottom of an ocean of air, where the air pressure is the highest at the bottom, and we have significant atmospheric pressure as a result. But it's nothing compared to the pressure animals that live at the bottom of our water ocean are under. And there's a little bit more I want to say about this since we have the time. So fluid dynamics is very important in galactic astrophysics, because what's amazing is we can treat gas clouds that form into stars with these same fluid dynamical equations. And what's even more, if we scale out far enough, we can actually treat the motions of stars themselves as if they are like a fluid. So we look at billions of stars moving in tandem with each other under like a gravitational force. We can use the same math that we use to describe a fluid and get a pretty good description of how these stars behave. And actually, a big amount of work that NASA does in studying galaxies and figuring out how our galaxies form involves making use of these fluid dynamical equations numerically. Now, it's not going to be exactly the same as a fluid dynamics equation that describes something simpler like water We're going to have to put collision terms in there maybe. Although a lot of stars, they're so far away from each other that they essentially behave as a collisionless system. So actually, usually collision terms aren't too important if we're just talking about the motion of stars. But even then, we can take these stars and we can modify the equations a little bit and get a great description for the behavior of these systems. So fluid dynamics for the field of physics is extremely important. And you'll see it used in so many different places. And actually, when you talk about electric and magnetic fields, the idea of writing equations that could describe these fields, they had their beginning points in the fluid dynamics equations as well. Fields are different. Fields do not behave like a fluid. I wouldn't say that. But they do obey certain continuity equations like fluids do as well. So the whole point of this is that we've got this differential equation that describes fluid flow. We got a couple of different ones actually. And we're going to play around with differential equations a little bit in this chapter. And we'll see how we can use these basic differential equations to solve for some very interesting variables and solve some very interesting problems. This is in some ways the most challenging chapter in the class, and in other ways the most interesting. But it's not as challenging as the entropy in other respects. So it's just kind of its own thing, but it does have a little bit of math going on in here. So here's a picture of the molecular models of gases and liquids. So we've got these molecules that are like pretty far apart, and they can collide with each other, and they can collide with the container. And the collisions with the container produces a type of pressure on the outside of the container, doesn't it? Yes. Why does it produce a pressure? Because when one of these molecules, which each one has a certain amount of momentum associated with it, collides with the wall, it produces a force, because force is the rate of change of momentum. So the gas molecule collides with the wall and changes its momentum in the opposite direction. But by Newton's laws, forces must occur in pairs. There must be an equal and opposite force. So the wall exerts a force this way on the molecule when it bounces off the wall. But the wall itself gets a force going this way. So the wall exerts a force this way, and the molecule exerts a force this way. The force this way produces an outward pressure on my container holding in my gas. So you can sort of figure out the faster these things are going, the more I heat this thing up. That's why the gas pressure goes up. So you take a compressed gas that's compressed inside a volume, and you start heating it up, giving it more and more energy. That thing could explode. Tanks can explode that way. That's why heating up like gas tanks can be so dangerous. It's because of that fact right there. Okay, so the liquid has the same thing. It has a well-defined surface though, because what happens is these things are moving so fast that the force of gravity is negligible. It's not enough to slow these things down and get them to like settle and have gravitational forces act on them. There's like an RMS velocity, and if the RMS velocity exceeds a certain quantity, then the gas will all escape. And that's what sets our atmosphere in Earth and makes our atmosphere what it is. If Earth was bigger and had a larger gravity, the gravitational force would be enough to hold on to gases like hydrogen and helium, because hydrogen and helium have RMS velocities that are like enough to escape Earth's gravity, but not Saturn and Jupiter. Okay, so that's sort of like the idea here. But with this liquid, these things aren't moving fast enough and don't have enough kinetic energy anymore to overcome the gravitational force, and so the gravitational force acts on them, and they all kind of settle at the bottom of this tank. And so they didn't explain that in this figure. They just acted like it happened magically, which is not a good explanation. So that's the explanation for how it actually happens. It's not that this liquid has a property called liquid, which always settles at the bottom. No, these liquids have internal energies which cause them to react differently in a gravitational field, and that's the reason. Okay. So then the detailed behavior of gases and liquids can be complex. Fortunately, we can capture the essential characteristics of gases and liquids in simple molecular models. A gas, as shown in this figure, is a system in which each molecule moves freely through space until on occasion it collides with another molecule or the wall. So the gas is compressible because there's empty space between the molecules to begin with, whereas that liquid, they were already packed in closely together. And similarly for a solid, although solids, some of them are actually like crystal lattices, like ice, you can compress it, but that's sort of like an exception to the rule. Typically with solids, you aren't going to be able to compress this. It's already packed pretty tight as well. Okay, so molecules are far apart. This makes the gas compressible, and gas molecules will eventually collide with each other or the wall of the container, causing pressure within the vessel. A liquid is a system in which the molecules are weakly bound to each other, but less strongly than in a solid. So the weak bonds keep the molecules close together, but allow them to move around. Liquids, like solids, but unlike gases, are essentially incompressible. The molecules are about as close together as they can get, and the molecules have weak bonds that keep them close together, but the molecules can slide around each other, allowing them to flow. And the molecules aren't really compressible. So we say that like fluids, they're not compressible, but they do flow. Gases flow and they're compressible. Okay, so there's properties of fluids, and we're going to be talking about each of these properties quite a bit. There's density, volume, and pressure. Density is the amount of substance I have per unit measure of whatever my measurement is. I can have a linear density, like a line density. That's just my density of mass or whatever per unit length. That has dimension of just 1 meters. I could have a density per unit area, mass per unit area. That's going to have units of kilograms per meter squared. And most commonly, I'm going to have just like traditional density, mass per unit volume, which is my kilograms per meters cubed. Then we have volume itself, which is just like we're all familiar with, how much space something occupies, and pressure, which is like how much force I have combined with area, okay? So those three things are going to be important. So first I have density, mass per unit volume in this case. And then while it's true that 1 meter is equal to 100 centimeters, it's not true that 1 meter cubed is 100 centimeters cubed. I think I already went over this calculation before, but I think I'm going to do it again. So if we have like a cube that has like 100 centimeters, in every which way, how do we convert that into meters? Okay. And then 100. So we have 100 centimeters cubed, and then there's how do we convert that into meters? Okay, so let's see. Let me do it exactly how they do it in this problem. Okay, so they say that 1 meter is 100 centimeters. It's not true that 1 meter cubed is 100 centimeters cubed. And while the volume is constant, 1 meter equals 10 to the 6th centimeters cubed. And a liter is 1,000 centimeters cubed, so 1 meter cubed is 10 to the 3rd liters. Okay, so we have 100 centimeters equals 1 meter. 100 centimeters equals 1 meter, 1 meter. And we have 1 meter in every which way. So if we have 1 meter cubed, that's the same thing as 1 meter times 1 meter times 1 meter. 1 meter cubed. But that's the same as 100 centimeters times 100 centimeters times 100 centimeters, which gives you that huge number for centimeters. So if I give you something in terms of centimeters, it's 10 to the 6th centimeters cubed, because it's 100 times 100 times 100. 100 cubed, 10 to the 6th, because it's 1 times 10 to the second, that's 100, and then cubed, these exponents multiply, so we have 10 to the 6th centimeters cubed for 1 meter cubed. So if I give something to you like 5 meters cubed, or if I give you something like more likely like this, it's like, okay, it's 100 centimeters cubed. How many meters is it? I have to convert it into meters for my units. Well, how do I do that? Well, I have to do it like this. 1 meter is 100 centimeters, okay? But that's just one of those centimeters. This is cubed, so I have to do that 3 times, okay? And that's going to give me my answer, okay? Or I could just do like, maybe it's only like 50 centimeters cubed, right? And then it's going to be this small number, 50 divided by this, and that's going to give me my conversion. So remember, when you're converting with volumes, you have to convert 3 times. You can't just do the conversion once, because you have a conversion from centimeters to meters or meters to centimeters in each direction in 3 different ways. So that can be kind of confusing. So I wanted to go over that with everybody. Okay. So there we go. That's the picture of how that works. So let's see here. A piece of glass is broken into 2 pieces of different size. Rank in order from largest to smallest the mass densities of the pieces. Well, of course, they're all going to be the same, because it was the same piece, and the mass density just is mass per unit volume, which is constant. So if we break it into a smaller piece, it's not going to have a different density. The density will be the same. The amount of masses will change because the volume changed. So this one might have a smaller mass than this one, but the density is the same. Okay, now we're talking about pressure some more. So water pressure pushes the water sideways out of the holes. When I make holes, notice that the water emerges at greater speed from a hole at a greater depth. Okay, what's that point that they're illustrating it? How do we know that this goes at a higher speed than this one or this one? How do we see that? Why is that? What's the evidence that, yeah? Right, so there's more pressure at the bottom. And then we can see, it's kind of illustrated badly here, but you can see that it has more velocity at a greater depth, because this line, these all have gravity acting on them, but this line, it goes out further before curving. So it has more tangential velocity going this way. It's like throwing a ball at a faster speed. It goes a longer path before being brought down. But then they might all end up at the same place, or roughly the same place, because this one has more vertical ground to cover than this one does. So this one gets brought down at the same point roughly, because there's this vertical distance is smaller than this. But it's going far faster this direction, so it still reaches just about as far. Okay, so this figure here shows a fluid, either a liquid or a gas, pressing against a small area A with force F. So we've got these forces pressing on these area, and this is the force that pushes the fluid out of the hole. And in the absence of a hole, the force pushes against the wall of the container. So we can define the pressure at this point in the fluid to be the ratio of the force to the area on which the force is exerted. So pressure is equal to force per unit area. So if I know my pressure and I want to know what my force is, I just multiply pressure times area and get my force. What's a nice way to see that and see how pressure works? Well, we can, and you're going to do this in problems. You'll have to use this kind of reasoning. So this is, even though this might seem basic, it's worth going over and exploring. So pressure is equal to force per unit area. So if I know the, let's say I know the pressure, and I say, okay, the pressure throughout this container is going to be equal to 101,000 pascals, or like 1 ATM, I think. So it's 101 pascals. Okay, what is the force? And let's pretend this is a cube, so all these sides are the same. What is the force? What's the force on top? If my side here is 5 centimeters by 5 centimeters. Tell me what the force is on the top of that container. See if you can do that calculation. Okay. Take some time to write it out. Just keeping an eye on seeing who's still writing, thinking about the problem. Give everybody just like another minute. Okay, so what we're going to do is we're going to find the force on this top by multiplying by pressure times area equals force on the top. And we know what the pressure is because it's given as 101,000. What's the area? It's 5 centimeters by 5 centimeters. So it's 5 times 5 centimeters squared. Okay? So 25 centimeters squared. But then I have to convert that into meters. Okay? So I have 100 centimeters in 1 meter, and then that squared. So my area is going to be 25 centimeters squared divided by, and then it's going to be this, 100 squared. And then that's going to turn it into meters. So centimeters cancels, and so I have area is 25 divided by 100 squared. So the force then is going to be equal to 101,000 pascals times 25, and then all of that divided by 100 squared. Okay. Any questions about that one? Okay. Great. So that's the basic idea of how to do force on a side when you have the pressure. Or you can go backwards and find the pressure if you have the force per unit area. You can do that calculation in reverse and convince yourself of that one. Okay? So then we can combine that and note that the pressure is a scalar, not a vector. So the force that a fluid exerts has a magnitude of P times area. So when I said force here, I need to be a little bit careful. I mean the magnitude of the force, not necessarily the direction of the force. Magnitude of force. So we put like little bars around it and say that's the magnitude of the force on the top. But force can be a vector. But when it's multiplied by the area, it becomes a scalar. So why is that? Why does force turn into a scalar? Or why does pressure turn into a scalar when force is a vector? Let me show you really quick. Because here's what it is. Let's say I have some force going this way. Let's say I have some area. This area has an area vector associated with it called dA. And the pressure is force dotted with the area vector. So the pressure is going to be negative in this case because my area vector is perpendicular to the surface, and it's just my magnitude of my total area. Magnitude of total area. But the dot product is like takes the x component and multiplies it with the x component of this. taking the dot product of two vectors gives me a scalar, which is equal to a pressure. And that's why, even though force is a vector, pressure turns into a scalar, because I take the dot product between my force and my area vector, and I get this pressure term coming out. So we just assume this is true for like forces that are like perpendicular to the area vector, that are perpendicular to the surface and parallel to the area vector. Okay, so that's a very basic definition, but actually showing you how it's derived about, you can see how if the pressure is going in some direction and it's not just in one direction or uniform throughout, we actually have a tensor. It's not a rank 0 scalar anymore, it's a tensor. But it could still be, depending upon that case, then it might not be a scalar anymore. But for these cases in this class, it'll always be a scalar for pressure. Okay, have a great weekend, and I'll see you all on Monday.